Hello, everybody. I'm Cam Dales, co-founder and president of Peak Energy. Welcome to IONS. And with me today, I'm very excited for this conversation. An old friend of mine, his name is Adrian Yao, has had a storied career, actually, in the battery space, both on the academic side and the industrial side. He's the one of the founders of a lithium-ion battery company called EnPower here in the U.S. He is the founder of an organization that I hope to talk a little bit about called STEER, S-T-E-E-R, at Stanford. And then for some unknown reason, decided to jump back into the startup world, rejoin his battery startup EnPower as the CEO. And so is, I'm sure, having lots of fun with that. So we'll dig into that over the next few minutes or hours, depending on how this goes. But Adrian, welcome to IONS.
Thank you. Happy to be here.
Yeah, maybe a couple of words of background, kind of your history. Take us through how you got your start in the battery space, and then would love to talk a little bit, maybe in the beginning here, about your time at Stanford.
Yeah. Well, I think, again, happy to be here. Thanks for having me. I think, like most people in the battery space, I think the start is by accident.
If we actually knew how hard it was, none of us would have done it.
Exactly.
How hard could it be? It's a plus and a minus.
Exactly.
That's how I ended up in the industry.
Yeah. So I founded the company 12 years ago, coming out of undergrad from Rice University.
Yep.
Certainly didn't know what the hell we were doing.
Right.
And
like most of us.
Like most of us, yeah. And I can talk more about that journey later on. But really started the company out of Houston, again, because of Rice University. Spent a year in, actually our first start was out of a U-Haul office warehouse space.
Perfect.
In downtown Houston.
Yep.
Right across from Specs, the liquor store. So in case things didn't go well,
very
you knew
appropriate
where to go.
In the early days. Yep.
And then we had our first office in formal lab space in NASA Johnson Space Center.
Very
cool. Through a journey, which I'll talk more about, eventually moved to Tennessee for a year to work with partners on the East Coast, and then moved to Phoenix, Arizona for 2.5 years when we had a pilot line. And then in 2020, the basically last couple of weeks of 2021, early 2022, that's when we acquired the factory assets of formerly Enerdel in Indianapolis.
Right.
And that was a building that was built in 2009 with ARRA funding from DOE. And that, of course, allows us to suddenly be able to manufacture cells domestically, and that's super exciting. And I was a CTO at the time, and that's also a time in which I transitioned into a board role and decided to come back to an academic setting, also going the wrong way. My journey has just been
backwards from the start.
But I came to Stanford to get a PhD that I never got. Because I started the company out of my undergrad. And that's really to scratch an itch in furthering the technical depth.
Right.
But also to explore kind of what is further out there.
Right.
And so,
tell me and us, our audience, a little bit about STEER.
Yeah.
And why, my question is, why would you go back to a great institution for academics like Stanford and then start an institute that is basically industry focused?
Well, I came back to Stanford partly to explore what I could do next. I certainly, of course, still wasn't deeply involved with EnPower, but was curious about what comes after lithium-ion.
Yep.
And was actually curious about some things like sodium-ion back in the day.
Yep.
And before I wanted to jump in, because I jumped into lithium-ion headfirst without knowing anything about lithium-ion, and having already kind of spent more or less a decade of my productive life. I wanted to be a little bit more judicious about the next journey.
And of course, you ended up exactly where you started.
We'll get to that. Yeah, exactly. But yeah, I just want to be a little more judicious about where I should really focus my energy, and do a lot of this deep thinking about the what to build before you dive into do the how to build. And I'm of a tendency to just dive in. And of course, the really hard part, as you guys know here, is the how to build. That's where you'll spend a lot of your hours in. But I think it's therefore critical to spend and give a little bit more time in the what to build. And that critical phase really can set you up for success or failure. So as I was coming back and thinking, okay, this is a great place to really explore some wacky ideas. It's a great place to figure out what I could do next. I wanted to spend some time focusing on what to build. And really, of course, anything in the energy space comes down to economics. And so taking my learnings in the commercial sector and trying to pair that with the rigor that comes with the storied institution like Stanford is really an interesting melding of superpowers, I think. And really that is how STEER got formed, in partnership with my co-founders of STEER, Will Chu, who's a deep battery expert, as well as Sally Benson, who just came back from serving time at the White House as the chief strategy officer of the energy transition. There was a lot of good things there. And sodium-ion just became the first question because of my background, because of Will's background, because of the relevance to the energy storage space, which is, of course, booming starting from 2022, as well as the criticality of supply chains. So it was really the perfect problem to really dig deep into and figure out, if you were to do sodium-ion, what would you do, right? Because, of course, sodium-ion, as we all know, is an umbrella term, just as lithium-ion is an umbrella term. There are many strategies underneath sodium-ion and lithium-ion that could work, some that don't work, some that make commercial sense, some that don't. And so if I were really to spend time in the tech dev portion, where, we all know hard tech is hard, technology development is time consuming, can we first sit down with pen and paper and go really, really hard on the economics?
Yeah, on the
and just figure out, can we predict the viability before we spend all this time and effort? And it is ultimately selfish for myself because I'm trying to figure out what my next journey is going to be. And so that was really the impetus of something like STEER. And we pitched this to the DOE early on, and we're very lucky to have their early support. So they tossed us seed funding. Basically, it was running a startup within Stanford, basically. And I think I have an itch to build things, and ultimately came out STEER with, which is a very interesting combination of industrial depth and connections and connectivity, which is critical. I mean, that industry academia divide, I think, needs to be worked on.
I totally agree with you. Yet. And so just to summarize for our listeners, so STEER is an acronym. What does it stand for?
STEER is not an acronym. It started off as an acronym, but I don't like it. So
now it's actually it's just a verb.
It's exactly. It's STEER. It's a way to help guide what to build, where to innovate, and how to
where to steer the ship in research and in company building and in where we want to put our development dollars, right? And I think noble goal and absolutely needed as we think about sort of industrial policy and how to be competitive in the world. And we'll get into a bunch of that, particularly in batteries, which has become such a big topic geopolitically even. Yeah. I've personally been an admirer of what you and your team have done there. The connections you've built with, let's call it the real world, I think were great. And you also, in my humble opinion, were willing to take feedback and listen to what you were hearing in the world, as opposed to, sometimes the danger of the academic world is that it's just very inward looking, right? And I have to admit, in the beginning, we were pretty mad at you here because, you took a look at sodium-ion from the cell level. And, I think the first paper you published was in Nature, like very early on in the sodium-ion sort of journey, trying to look forward and trying to look at, are there cases where this could make sense and when and what has to happen? And there was a lot of nuance to that. And I think we agreed with much of what you were saying. I mean, I don't want to delve into that too much because I think there's a lot more history that has come from that, and you've talked about it before. But if I summarize it the way a journalist would, Stanford says that sodium-ion batteries will never be competitive. I don't think that's what you were actually writing,
No.
and I don't think that's what the conclusion was. But that was what was out in the world, and those, I know I personally got that question from like 5 different journalists.
Yeah.
But what I thought was really interesting and surprising in some ways was that was sort of where it started, but then you brought it through, or you developed the institution of STEER to be what has become it may not be a very famous group and industry organization, but I think it's become one of the most influential in the industry, primarily because I think, complementing you and your team, but probably especially you have been able to bring really, I think, some of the most important thinkers in the space together for some of the conferences that you've done, which has led to feedback, which has then led to conclusions that maybe are a little bit different than they were before. So can you walk me through that journey of, and I know a little bit about your background. You and I have been friends for a long time, so I'm cheating here a bit, but how the initial view around the cell technology of sodium-ion evolved into a broader view that ultimately became part of your PhD thesis, I think, right?
Yeah. I mean, I think the founding and the start of STEER is really kind of in parallel to the founding of Peak.
Totally.
I remember,
yes,
we were in Eclipse's office.
That's right.
Down in Palo Alto.
Yeah.
And that was right when I had first, done some modeling, and you guys were just starting. And then I was like, hey, this is what I'm finding.
Yeah.
And anyway, it's just been a fun journey. And yeah,
you're right, though. It has been a parallel, collaborative set of work.
Yeah.
That I think ultimately informed a broader conclusion.
Yeah. And I genuinely hope, and I do think that it has steered the industry towards more of what I like to say, technological pragmatism.
Yeah.
And that is something that I think generally we tend to lack.
Yeah.
Particularly in the West. Yeah. In the West. I think we are very enamored by R&D. We are very enamored by material science, which is the field I come from. But and actually, it's a point to say that we have to focus at system scale. We have to focus on what is actually commercializable. But in general, I do think that hopefully that overall effect has come through. But of course, if you want to do something, if you want to focus on and do a full deep study on sodium-ion, you need to start with the ion, right? You need to start at the thing that gives it its name. But then you cannot stop. You cannot stop there. Yeah. And really, the journey of going from looking at cell level economics to then system level economics, and not just system level costs, but also system level financial viability. That is the 3 chapters of my thesis. It's available online.
Oh, is it? Has it been published?
It is published in my thesis form. So you can go download it.
Brandon Kelly, our head of R&D, the one question he wanted to ask is, when are you going to publish your
Well, it's
PhD
already published,
thesis?
so I'll point you to it.
I'll
link it in the show notes.
My work here is done.
But yeah, so we had to walk through that journey, and that journey was very much informed by people like yourself, right?
Thank you. Yep.
Very much of the central identity of STEER, which you can think of as a think tank, is really to pair this really deep technological nuance with economic rigor, but really pair that with deep integration and feedback from industry. And I think something that I'm proud of for STEER in terms of the identity, and I hope this comes through, is being disarmingly humble. And I think that is critical, because certainly nobody has all the answers. And the benefit really is, if the superpower of the technical depth and the economic rigor only manifests if you can pair that with actual feedback from the practitioners in the front lines.
Yeah. Yeah.
which is yourself and other sodium-ion companies,
Yeah,
and hearing
well,
directly from
well beyond me. And I think you guys did a great job of engaging not just folks who were in the, let's call it the cell or the battery or even the system level, but, customer side of things,
Mhm.
IPPs,
Mhm.
The utilities themselves.
Yeah.
You brought together a really broad
Yeah.
cross section of voices from the whole industry, which is pretty unique.
Yeah.
Like,
Yeah.
I don't know of another organization that does that.
Yeah. And I think baked into that identity is basically that we embrace being wrong.
Mm-hmm.
And
So are you
'cause
saying you were wrong about sodium-ion batteries?
I think we're all wrong about something. I'll be the first to admit that we're all wrong about something.
Yeah.
The idea is to get less wrong,
Yeah, over
right?
time.
And so in the first sodium-ion gathering or convening that we had,
Yeah.
again, the question that we always ask is tell us why we're wrong.
Yeah.
And it's not necessarily tell us why. It's not necessarily that we're wrong. It's just that, okay,
What are we missing
yes,
here?
but what are we missing?
Mm-hmm.
And a lot of that feedback in that first, I remember it was tax day, 2024. It was April 15th, 2024. I remember that these events get kind of ingrained in your mind.
Right.
That's when we had that first event, and it was good feedback from industry people like yourself and saying, yes, but.
Yeah.
And the but was, okay, at systems level, there's a lot of nuance there that we got to focus on. So in the beginning, we based on also my background of being deep in the cell level technology, that was helpful for us to chart the roadmaps of, okay, which types of sodium ion, what chemistries,
Mm-hmm.
what design parameters, and what things can people do on a spectrum from those in the lab to those in companies that are commercializing, can really focus on the low-hanging fruits and the big goals,
Mm-hmm.
to really change the equation and then actually get to a point where you beat LFP, for example,
Mm-hmm.
head to head on cell level costs.
Which you have to do.
And so they're the initial the thing, and somewhat of the quote unquote dogmatic truth. The first dogmatic truth that I think was worth challenging, that I think often flies under the radar, is that low cost materials don't automatically equate to low cost cells. Right, dollars per kilowatt hour.
Yep.
Is a combination of dollars per kg
Yep.
and kgs per kilowatt hour. Right, that last portion, the inverse of which is energy density, and in general, it's just a metric of materials intensity.
Mm-hmm.
Both of them matter.
Mm-hmm.
And so increasing cell level energy densities is an important way to improve cell level costs. Now, of course, when things that require a lot of nuance gets published, there needs to be a way for this to bubble up into the sphere of the layman. And that's where I think a lot of this is, I think, still an important place for us to focus on, is how do you message accordingly and not overhype either answer, because the answer wasn't sodium ion is not competitive.
Right.
It's just that certain directions for cell level absolute head-to-head competition or advantage requires certain things to be true on the materials and innovation side, which we just talked about on your plant tour.
Right.
And that would be great if you could achieve those things. But it doesn't mean sodium ion on its own, not inclusive of everything else, is not competitive. So that was the first conclusion.
And it's a difficult. You're right. The messaging part is extremely hard. In our modern world of journalistic deadlines and sound bites and things like that.
And as someone who, like, again, I'm very much I'm at that point an industry returnee, so to speak.
Yeah.
That knows that the problem in this space, in the energy space, is not always, and in fact, most of the time, is not R&D.
Yep.
I didn't like that, the answer comes out to be more R&D is needed. I mean, I hated that was a message, but more R&D certainly is needed at cell level to get to absolute cost competitiveness, as is true always. But then the ability to then graduate above that level to the system and then to the financial viability portion is what came after. And naturally, there's that sequence of discovery.
Yeah.
And
we were on
really,
this parallel journey with
exactly.
you too, because I mean, we started the company with the thesis that sodium-ion battery cells were going to become more cost-effective than LFP.
Mm-hmm.
And we're, I think, on that road now.
Mm-hmm.
We actually pretty well agreed with your methodology
Mm-hmm.
and, the work that you did, which I thought was excellent,
Thank you.
and rigorous. Our main disagreement was like, when is that crossover point going to happen?
Yeah.
And I think from our perspective, we, with the benefit of probably 18 months of visibility into the industry that you didn't have when you wrote the paper,
Right.
we were looking at a starting point of cell cost that was quite a bit lower than what the assumption was in the beginning, and so that makes your learning curves go different, speeds and things, all of which turned out to not actually be the point.
Yeah, exactly.
And
I think the important message there is, and it is a message to every technologist out there, is that, sure, we all know economies of scale and the learning curve and so forth. We all know that's a phenomenon. Just don't blindly bank on it, because there's a place where it applies. And actually, as we moved on into the system level and even thinking about EPC, manufactured goods follow a positive learning curve, but construction follows a negative learning curve. I mean, it follows inflationary pressures. So then you need to be just don't assume that when we get there we'll get to scale.
And this is something that is pretty interesting, because the application really is the paramount question to ask within many of these technology problems. In our case, it's how much does a project cost over 25 years? And that is pretty different from the way we've organized our R&D, particularly in academia, where it's like material science, or it's mechanical engineering, or it's siloed into these specific things. And in the case of the technology we're talking about here, sodium-ion, the world is organized to talk about cells and cell cost.
Yeah.
It's also got a mindset of electric vehicles, because that's been the biggest application. Then you start to move into stationary storage. It's really not about that. It's about the whole project IRR.
Yeah.
Which is a conclusion that we came to on our own, I think, in parallel to you guys also really pushing the envelope there. And I must say, the work that you did is way more rigorous, and I think maybe appropriately for coming from an academic background, more, I don't want to keep using the word rigorous, but that really was it is. I think your analysis was very good. And I'd love to have you just kind of walk through, in a high level, the conclusions that you came to kind of bring to life these concepts that we're talking about in terms of cell versus system versus project, and why that matters, and how ultimately we can apply that type of thinking to not just this particular problem, but other problems.
Exactly.
I know STEER has a much broader lens than just batteries, right? And would love to hear a bit about that too.
Yeah, and just kind of continuing along something you just mentioned, there certainly is a bias, right? There certainly is a material-centric or an R&D-centric or a cell-level-centric bias to when we think about battery cells. And a lot of that bias is driven partly from the R&D side, from academia, and then a lot of that bias from the commercial side is from the EV world. And you have to, it's quite interesting to think about, because in the EV world, ultimately you care about selling a car. And the consumer sees one price point, and then they make that decision, and then it's theirs to handle, right? That's not the case for almost every other battery application, apart from consumer electronics. It's a similar case, right? I mean, an EV is a consumer electronic, big iPad on wheels, but in things that need to make money, that is not the case. The lifetime performance of it is critical to the ultimate economic decision of whether this is a good idea or a bad idea, regardless of what CapEx in the beginning is. And so to some degree, EVs are more very CapEx biased, whereas other things are going to be a lot more OpEx biased.
The EV companies have struggled to convince consumers to think about total cost of ownership of
Yeah.
the product. Like,
Yeah, maybe there's, exactly.
this has
that could
been
be
an
something.
economic argument for 10 years
Yeah.
around why EVs make sense, even though they cost more at point of sale. You don't have to maintain them,
Yeah.
nearly as much. You don't obviously pay for gasoline,
Yeah.
electricity a lot cheaper.
Yeah.
Um,
Yeah.
But it's hard to get a consumer to do a total cost of ownership analysis.
You think?
On the other hand, it is really not hard to get a utility
Yeah.
to think in those terms, because every single
I mean,
project
they live
do.
and die by that. Yeah, exactly. So, I mean, to answer your question more, and for the audience about the journey,
Yeah.
I think my journey was really about challenging 3 dogmatic truths, so to
Mhm.
speak. That first one I already talked about, that low cost materials automatically translate to low cost batteries. That's not true.
Mhm.
There's a nuance to it, and you got to look at it. The second is, and I'm sure you've heard of this a lot, is that energy density doesn't matter for good scale storage. And I think intuitively it makes sense because land is cheap and so forth. It's not about land. It's really about construction costs.
Totally.
And when you think about just the level of energy you can stick within a given container, if energy density didn't matter, then we wouldn't have seen the container level energy density of energies of LFP go from less than a megawatt hour to 2 to 4 to 5 megawatt hours in 2025 to now 20-foot systems that are basically 10 megawatt hours and more.
I completely agree with you that is the biggest lever to reduce cost across the board. And I think the game, all of these things are balances, right? Because like, yes, low cost materials definitely are a good thing, but it has a penalty in terms of energy density.
Not necessarily, but it might have a hidden penalty.
Yeah, which would drive up manufacturing costs. And so you need to be so low that you're better than the penalty. And I think energy density is the same thing.
Yeah, exactly.
Energy density does matter, even at the site level, primarily for construction costs. And there are certain, let's call it, parts of the broader stationary storage that really does care about energy. If you're putting, batteries inside of a building in your city or something, there's a real footprint question. But by and large, it's a cost driver. And so I think we would look at it and say you can afford to have a lower energy density to a point.
Yes.
But it has to give you a cost advantage against all of the disadvantages that come along with that, construction costs, et cetera.
Yeah.
And all these things are traits.
Yeah. And that turns out to be a logarithmic correlation. So, a half megawatt hour container, well, it doesn't matter if the container were free.
Right.
The construction costs of installing that with the DC cabling and the concrete pouring and the trenching and just like all the unsexy stuff of just going
we think that's sexy. Just saying.
I think it's super sexy. I had so much fun going into every step of digging a trench. Anyway, probably more detail than anyone had to go into, but that ultimately, again, if you had basically a half megawatt hour container that's 20 foot, just as a de facto standard, your construction costs end up being several $100s per kilowatt hour.
Right.
And so that rules out, it helps actually rule out chemistries.
Yes.
And as a technologist,
and there are chemistries out there, non-lithium stationary storage chemistries that really
they don't make sense.
They're not going to hit the mark ever.
Yeah, unfortunately. But I actually think it's a blessing as a technologist, or as someone who is thinking about what should I dedicate the next 10 years of my life doing. Either be it your PhD thesis or a company in which you're starting.
Right.
You got to know.
Yeah.
Right? Because having that answer is hyper liberating.
Yeah. We call
being able to cross things off.
Facing the brutal truth.
Yeah. Crossing things off and taking options off the table is one of the most liberating things as a technologist or as anyone. I mean, even an artist with a constraint is going to be actually can leverage and capitalize on that constraint. So anyway, that was a very interesting takeaway. And the reason why this became so important is that we're also in a paradigm now where the cell level costs, which we are addicted to, we tend to get addicted to, is not the most important line item anymore.
That's right.
In LFP, we have cell costs that are less than $50 per kilowatt hour, but construction costs, EPC in general, is 50 to 70. It depends on where you are. There's regionality to it. And again, it's inflationary. So now the cell is not the most important thing in terms of a line item. So that's the reason why that was the impetus for really deep diving into that.
And the way we think about that is that 3-4 years ago, total project cost over its lifetime, including OpEx, which is a big piece, was called $500 a kilowatt hour for total cost of the project. And more than half of that was cell cost. And then over the last 5 years, cell costs have come down so dramatically, certainly driven by LFP, but, other technologies like sodium, which are built on the same manufacturing platform, follow that curve kind of, mostly. And so to your point, now the cell cost is actually not even in the top 3 or 4 cost buckets for the project. Number 1 is OpEx. Number 2 is, construction and installation, right?
Yeah.
And that's the thing that we as innovators should be working on.
Yeah.
And I think there's a hint there too for the question that I want to talk about towards the end of our chat here, which is how can we in the West, American companies, we're both running American companies now, how can we compete against the juggernaut that has been built in China based on scale and making things at scale? And I think there's a hint there around the cost economics are no longer about the widget, the cell. It's around how do you implement and run these projects at home, where that's where the money is today. Yeah. And so attacking that is at least one answer to how do you compete against CATL.
Yeah, yeah. I mean, you brought up operational OpEx.
Yeah.
And that's a good segue into kind of the third dogmatic truth, right?
So
and that is
the first was
low cost materials don't result in
low cost cells
batteries
necessarily. Yeah.
Right. Energy density doesn't matter for the grid is false.
Yep.
The third is, at the end of the day, we don't go out and build stuff just because it's cheap. We build stuff because they make financial sense. And so cost is only half the equation, right? You got to look at the revenue side, which is kind of what you're talking about. And okay, now that you've bought the thing, what is it going to do? And that's really where we need to get into really understanding the use case throughout the lifetime. And it's going to be application dependent. And so in certain things like EVs or grid storage, they're going to be different lenses in which you have to look at them. And ultimately it's the viability, economic viability that matters. And something that I really don't like as a metric that I think does us disservice to focus on is the so-called levelized cost of storage, which was borrowed from the levelized cost of energy metric, which is used for mostly like thermal plants and for power generation. Batteries don't operate the same. And the problem with it is that it's a cost-centric, again, it's obsessing about costs, not about value. And what we need to pivot ourselves into is really thinking about value-centric metrics.
Can you give a very specific example of that in the world of batteries that we're talking about here?
Oh, have you heard of sodium-ion? So
what I mean to say is, there are let's make it concrete. Like what are the costs you're talking about, and what are the value metrics?
Yeah, I mean, this is of course dovetails exactly into peak strategy, which is why I'm excited to see you guys out here. Is basically every project has what we call a cumulative present value curve, or eventually a band. We'll get into that later, but it's basically this Nike-shaped curve, right? The Nike-shaped part, the dip in the beginning, is basically discounted cash flow, right? You're spending a bunch of capex, and you're digging yourself into a spending trench.
Buying batteries.
You're buying batteries,
making
and you got to
construction sites.
Go make it, right? Yeah. And the depth of that, what I call capex well, is obviously going to be dependent on the cell costs, which are not the most important thing anymore. It's also going to be dependent on your site level energy density, and again, the energy density of your containers, right? And so that will pull you down into your capex well. Now that you've built the thing and you turn it on, you have then the longevity of that project to make back and dig yourself out of that hole. Right?
It's a great way to think about it. Yep.
And the break-even line, the break-even time, of course, is when you cross over the zero line, and that's the net present value equals zero line.
Yep.
And so every technology and every project is going to have, and this is true not just for batteries, but also true for a nuclear plant. It's true for anything you put down as, and think about in project finance terms is you have, again, the CapEx well is one feature. You have the what we call the slope of the revenue recovery period. That's the portion of digging yourself out, this long tail of the Nike curve.
How tilted is the swoosh?
How tilted is a swoosh.
And you want to be on the top part of the swoosh, not the bottom part of the swoosh.
Well, you're going to inevitably have to come out of that swoosh, and you want that to be as steep as possible, right? And then of course you have the longevity of the asset that dictates when do you stop, and you can just call it an end. That final endpoint and its relationship to the zero line is your net present value, right? Your discounted, net present value, and of course the crossover point to the zero line is your payback period. And if you change your interest, your weighted average cost of capital to whatever, push that net present value down to zero at the end of the project, that's your internal rate of return, right? This is a good visual way to think, and I think
it's a great way to think
every
about it.
engineer going into grad school or anything should think like this.
I was going to actually ask you about that, because I know for me personally, and I'm not a wet behind the ears undergrad anymore. It's been a long time.
I can't tell.
And but I had not actually ever in my career up until now really run into project economics and how to think about the economics of these things.
Yeah.
Is this something that we are teaching our next generation of technologists formally?
It's going to be.
Does Stanford or Jane Woodward's class at Stanford have a module on project economics, and we're going to drill this into people's heads?
Absolutely. Yes.
Yeah, I think that's so important.
It is so important.
In the energy space, for sure.
It's just as important as Physics 101.
You're right. It's the physics of money.
Because if you think about a technology, everything related to, just take any energy storage device as an example. We spend a lot of time thinking about, should I use nickel? How much nickel can I have? They're expensive. It's a critical mineral. The price of what nickel is whatever. That's all on this first portion of that CapEx well.
Yep.
And that dictates how deep you go.
Yep.
But myopically focusing on that is not productive, because if an additional percentage of said additive that might pull you down deeper in the CapEx well gets you better operational efficiency, round trip efficiency.
Yep.
Then round trip efficiency is directly tied to the slope of your revenue recovery curve.
Yep.
And so there is a trade-off. There is a right amount to right size the material science that you're doing. And it's not to say that material science is not important. It's just that you have to right size your problem with the economics at the end of the day.
Yeah. Yeah.
And that's just one example. Like,
it's a great point, and it's something that has taken us some time to instill a culture around. So literally in our R&D labs, when a scientist proposes they want to go work on this project, we force them, and now they just do it because they know that that's how the decisions get made. We force literally running the full IRR analysis of a project with like this new molecule and the electrolyte as an example. Like it literally is at that granular level. Okay, it's going to cost us 2 extra pennies per kilogram. Okay, what does that mean? How does it change the RTE of the cell? How does that affect the revenue that can be generated? And so we have a whole modeling exercise that we've invested a lot into in order to help our scientists decide which way to steer the product.
There you go.
Based on project level economics, which is not how any of us would think about it.
I'm so happy to hear that.
Yeah.
That is, well, if you want to know how, go read my thesis.
All right, you hear that? Go read the thesis, guys.
Yeah, but also I think what's super valuable for technologists and engineers and so forth is that you can actually put a dollar metric on what you're chasing, right?
Yep.
Because again, we are so focused on CapEx, but every percentage of RT round trip efficiency improvement, because of either electrochemical behavior, hysteresis, conductive additives. I mean, we can get real deep here in terms of like, okay, how should I be optimizing my formulation for low DCIR? that has a cost, and you can quantify in a net present value term, in a dollar per kilowatt hour, end of the day, not in a capex term, but a net present value term. And so then there's a delta percentage RTE, delta NPV, and you can quantify it. Is that more worth my time than to extend delta or improve delta cycle life, delta NPV?
Yep.
And now you can really surgically go address these problems that, it might seem less sexy, but ultimately it's not. I mean, my goal is to...
You want to work on things that really matter.
They matter. And what matters is what's sexy. And you got to use economics to make it sexy.
Right. And, there are certain applications where that gets even magnified, right? So one of the reasons why we're so excited about data centers and, big energy storage installations behind the meter with a data center, and why we think sodium is a great way to go there, is because that efficiency advantage, which partially comes from you don't have to run air conditioners and the actual RTE of the cell, all that stuff, directly correlates then into value and revenue that a data center can produce.
Yeah.
Because a data center is limited on what? Energy.
Yeah.
And so every electron that is not going into producing, a token because it's running something on your system or because it's getting wasted in the round trip efficiency in the cell is an electron that doesn't get turned into revenue through a token. And that magnifies that, additive to the electrolyte by a factor of 1,000 or something like that, right?
Yeah, exactly. And this is a world in which industrial use cases of batteries do care about the total cost of ownership or the lifetime economics. And I'm sure we'll talk about it later. I mean, that is also the direction which I'm manufacturing for, right? The industrial robotics and those chemistries, or the things that we go after, are going to be the applications where you're not necessarily, in some cases you are, buying just for CapEx, but you have to think, you have to be technically savvy to figure out what market to go after. And I think if those that are technically savvy can grab a large part of the market. And I think this comes back to your point about how to compete with China, is you have to be technically savvy and
economically
you can't just focus
savvy.
on economically savvy in the context of the region in which you're in.
Exactly right. And I think that's one of the key things that we're trying to work on is in the market we happen to be in, highly complicated set of multiple utilities with challenges and costs that are quite different than what they are in China, right? Labor costs are totally different. Like
EPC costs.
How much does it cost to do a truck roll, right? Like, and so being close to the market and using those insights by just living here and having to work on projects here, those are the things that ultimately give, I think, American companies an advantage, whereas just competing head to head with CATL on scale and cost of making the cells that are coming out of the factory is really hard to do. So
you don't say.
Yeah. So let's transition then a bit. Thank you for all the work you've been doing at STEER. We're a giant fan of that and hope to see it continue long beyond your tenure there.
Yeah.
So you get your PhD, and instantaneously you, instead of going off and doing something totally different, you're back at EnPower. Why? And I don't mean that in a derogatory way. I'm really interested in your journey of how almost all of us, we go out into the world and then, to find ourselves back at home. So tell us the story.
Yeah. I'm super pumped. And so, let me step back. I think being at STEER, and this is how I like to paint it. It's an image I have in my head that might make sense.
Yeah.
Coming from spending, close to a decade in industry as a founder, and I'm sure you're in this right now and been in this kind of position in the past, is when you're in your company, you got your horse blinders on, right?
Yes.
All you care about is
make payroll.
Seriously. Yeah, we got to go.
One day I'll tell you a story about how we almost put the payroll of one of my companies on our credit card. We got saved by a customer. That'll be a good story to tell.
Nice.
Yeah.
But yeah, and that is a mental shift that I think I was very cognizant about. Is the split second you go from I'm considering to no, I'm doing this, that this is now my company and I'm going to go do it.
Yeah.
Your your mental shift is massive. It could be 2 seconds apart, but your world view has changed, and that you just care about execution, and that's good. That's what you need. You need this this crazy focused mentality, and this is why I think there's a real good symbioticism between an entity like STEER
Mm-hmm.
and the industry, because you can be the unbiased, objective, third party, neutral
Yeah.
kind of validator.
And you can think more broadly.
And you can think more broadly and really try to prevent and pull people out of no, that path is maybe a little fraught, or that you got to think those through. And this is what you have to believe, the set of beliefs in which need to be true for your thing, whatever widget you're doing, to come to life. So anyway, the thing I like to anyway, when you're in that founder mentality, you're kind of like a fish in swimming upstream, right? You're like a salmon trying to get to the whatever they do. I should think this through a little.
This is a family show. We don't want to really get into that.
Sorry.
What the salmon do when they're spawning.
Yeah, so you're swimming upstream, and you're fighting the good fight. I think the value of being in an entity or in a position that's STEER is that, yeah, you're not a fish. You're standing on the bank of the river, and you can see there's a fork in the river, or there's a bear there, so don't jump because they'll snatch you. You have that kind of bird's eye view from the side of the river. You're not a practitioner, but you're an observer, and you can help steer the pathway, right? And I think operating or occupying both of this, what I call the builder's world, as well as the intelligence or strategic world, is a real luxury to have. And as a builder at heart, there's always this desire to go back to being a fish, and maybe having been enlightened by some of what you've seen on the side of the river, is like, hey, no, I kind of know which direction to swim now.
Yep.
And every time as a board director going back to see my company, I also have that itch of just, man, I miss this equipment. I love just manufacturing and the people, and just like the just overall
fighting the good fight is important too.
The overall effort to just go build. So anyway, come time after I finished my PhD, and I look at the market context, I mean, there is a world in which, I mean, the world has shifted completely underneath our feet in the battery world. And certain stars have aligned that have kind of been 12 plus years in the making. And so looking at where we are, I really do see few companies in the cell making space, domestic lithium-ion cell making space, as well positioned as we are. And right now we are one of the only end-to-end powder to cell makers that is right size for the markets, and which define the next generation of autonomy, and the next wave of critical technologies. And there's what I call a missing middle strategy in which we're going after. And basically that is, we have to be able to focus and serve the markets that are currently too small for the commodity giants and the incumbents to purpose build anything for, but also too big for the niche specialists to make at cost, because cost still matters.
Yeah.
And mechanistically, this is what I call building the ATL of America. For those in the battery space, ATL is what preceded CATL. And I think part of the hubris, if I may, in the West over the last decade is that we've so often tried to chase this. We're going to build the CATL of America or of the Europe, right?
Yeah.
And you just have to understand that doesn't come from nowhere. Even CATL didn't come from nothing.
100%.
It didn't spawn from thin air. It came from ATL, which really learned through making the stuff that nobody else wanted to make. And if you kind of dial back the clock, it was in 2003 when a new category of products came, and that was the iPod.
Yep.
And that's a world in which commodity cells at the time, 18650s, which remarkably we still have today, just didn't cut it, right? Because Apple had a very different vision for how the product should look.
Yeah.
And so it really took a hungry startup at the time to kind of raise their hands and say, no, we'll do it.
Yeah.
We're going to eat the pain to go figure out how to make the stuff in which you want to fit your product vision and enable this. And of course, they made a huge correct bet. The market took off. It obliterated, digital cameras. Smartphones topped 100 million devices in per year and in a really rapid time. And that's how a star was born. And so today, I see a very similar story. It's not the iPod today, but it is autonomous systems and critical infrastructure. From drones to industrial robotics, the unsexy kind to the sexy kind, like the humanoids and quadrupeds that we're all talking about. And of course, data centers. And there's both a play inside the white space and inside the black space, right? And where you want to play is strategic. And again, this is a world in which commodity cells just don't cut it because of size, because of weight, because of power, because of safety, but also very importantly, supply chain. And that has never been as remarkably sovereign of a demand in kind of my journey and my career.
Yeah,
and that's really the opportunity in which we're taking. And so it does take a hungry upstart.
Yeah.
And I see us EnPower as that hungry upstart.
That's great. And congratulations on, positioning the company, I think, correctly. A lot to unpack there. You talked a bit about how to get big, you got to be small first.
Yeah.
Going from zero to big
Yeah.
doesn't really happen. Even CATL
Yeah.
started small.
Yeah.
Right. The introduction of new applications create space for new companies doing things better around that particular. And I would argue even energy storage is true. That's true. And it's part of our thesis that, grid storage was really not even a thing 3 or 4 years ago, which was a shock to me because in batteries, we've been talking about grid storage for decades, but I think the statistics were something like when we started the company, less than 2% of what was going to be installed on the grid in the next, 7 years had actually been installed on the grid. And even today, the vast majority of LFP systems on the grid today have been operating for less than 18 months. It's like 60% of the entire fleet.
Yeah.
And so it really is quite the beginning of a new industry, really.
Totally.
And that's what leads to the opening of a technology or a company that is focused on that can maybe do it a little bit better.
And purpose built for it, as you are purpose building something specifically for passive cooling or passive cooling for a grid asset that needs to last 20 years, and you're thinking about it as a dedicated 20-year asset or 25. I don't know. That
depends on the customer.
That purpose built is the risk that you can take as a small company initially. And you guys are pretty big,
and you try to be the best in the world at that specific niche that you're going after. This is back to like good old Jeffrey Moore and Crossing the Chasm, right? So, I'm interested also then to dive in a little bit more on the target markets that you mentioned, particularly around autonomy. A lot of really amazing things coming out of Silicon Valley and really all over the world. Talk about your strategy, if you can, a little bit about what that means for the type of battery product that you are making and how you think you can differentiate yourself through focus on those markets.
Yeah. So people that know me know that I hate the term Holy Grail for batteries. I just think let's just all, if we could, delete that from our lexicon. There's no such thing, right? You're going to measure every battery on a multi-dimensional spider chart, 12, 13 axes. You can pick your own kind of metrics. And they're just different shapes of spider charts. LFP is one in which occupies extremely low cost, great cycle life.
Mhm.
Obviously, energy density is not there and can't compete with NMC type products and so forth, so on and so forth. I mean, basically, it has a shape, and that shape certainly has a lot of things in which it can serve, but it's not for all. And similarly, in the fascination of the West for a long time now, which I think has been largely misplaced, is solid state, and really exactly what even that means is very blurry, because it's not, again, it's an umbrella term that doesn't really have a clear definition of what exactly is.
Yeah.
And ultimately doesn't. Nobody cares.
Right.
Is it solid or not?
Right.
Nobody's running that purity test. Ultimately, what you need to serve is a shape of an envelope that serves a need. And so today, that is going to be in the autonomous space, high energy, high power, and sometimes, in some cases, ultra high energy, ultra high power. And you're okay sacrificing energy if something, for example, is repeatedly charged and has multiple cycles per day, like warehouse robotics. And
Yeah.
that's a world that has a different spec than a drone that needs high energy density. It doesn't need fast charge, but it does need high discharge rates. And it might not need to last that many times, right? The average cycle life of drones is quite low, depending on, of course, which application you're in. If it's
Might be one.
Or two, yeah, exactly.
Yeah.
And whereas intelligence, surveillance, and and reconnaissance type robots or drones might be more in the 300 to 500 cycle range, but certainly not 10,000.
Yeah. And then gravimetric versus volumetric.
Yeah, volumetric. And so anyway, all of that is a space in which the incumbents that are mass manufacturing LFP and even the EV batteries don't necessarily serve. And so
it's still a one product fits all mentality.
It is, yeah. And so again, taking this approach of what is a moderate volume, moderate mix player that's addressing this missing middle strategy as EnPower is, what can we do that is purpose built for this application space that doesn't require you to give up on cost nor performance? And being able to hit those both
is the strategy really to pick a handful of applications, which, when you talk about autonomy, it feels like it was a relatively, compact vertical, but then as you explain it more, you realize actually there are vastly different sets of requirements for even kind of related, looking things, whether it's a robot doing this or it's one that's flying there. Or
exactly. A drone is
with massive differences of energy density requirements, cycle life, power, etc. And so that the idea is to pick a handful of these smaller markets, build cells that are the best set of trade-offs for that particular. Okay.
And that is a moderate mix, so to speak.
Yeah.
By mix, I mean product mix, right? Moderate volume, moderate product mix. And your ability to be flexible.
Yeah.
So again, the ATL strategy is what gets you the ability to also, I mean, it's like a VC. You're making multiple bets.
How do you think about the timeline and the ability to customize the product in a time frame that can make money? Because I think certainly 10 or 20 years ago, we as an industry probably didn't know enough to know how to just a priori dial in this combination of factors. And then there was a lot of trial and error. It would take a long, long time to actually have it hit all its specs. Cycle life, of course, is always a very long process just by its nature.
Yeah.
Do you think that we are at the point now in terms of the tools we have at our disposal, digital AI and otherwise, rapid testing, all this good stuff, simulation, that we can, in a reasonable time frame, design custom cells and make money doing it?
I think my answer is, I think so. But actually, I think the more important answer to that is not technical. It's commercial. The markets that we're talking about, and this is part of this aligning of multiple stars, is, for example, when you're when you're looking at drones as a launch point, pun intended, I guess, um, the cycle life being less than 1 to 300 or 500 is part of that success story, right? Because you're no longer needing to prove 5+ years of cycle life
For sure.
for an automotive application, or even more for
Right.
a grid scale energy storage application. Your iteration cycles are very fast. The Ukrainian drone development cycle is about a week, and we have to be able to. A week is crazy fast for insanely fast for batteries, and it's not like we have to meet that, but you do need to be accelerated. And these are markets and the commercial opportunities that does have the flavor of being able to address quickly, and allows you to fail fast.
Yeah.
And so that is a feature, right? Of not a bug of
Yeah.
this commercial strategy,
So on a commercial
and also
side,
understanding who really
yeah.
is who has power.
Mm-hmm.
Because in the EV space, I think there's a recognition, or I think a lot of the domestic players, be it on materials, which I think we've overinvested in, have catered to OEMs. But ultimately, who has the power to actually integrate it is not necessarily the OEM. Because we are living in a world of an oligopoly of very big cell makers that can actually do the thing. So they have control, and really understanding who has power in the value chain. It's not always at the end of the value chain.
Yeah.
You need to know who has power.
Do you think that your model over time becomes more product centric in the sense that you'll offer, pick a number, half a dozen different types of cells where people will just mostly be trying to buy that thing? Or do you see yourselves as being very much customer oriented? We're going to build a purpose built cell for your application. It's more project oriented.
Not that. I think that is where you begin to get into more of the realm of niche specialists and custom cells and bespoke products. And that's certainly an area where we don't want to occupy.
Okay.
So it's actually a very interesting question, because the hardest thing for us to change, or for cell makers in general to change, is not the chemistry. It's the footprint. Are you making a cylindrical, prismatic, or a pouch cell? That's a $30 million investment.
Yeah.
Just to do one of these things.
And what do you do today in your factory?
We make pouch cells.
Pouch cells, yeah.
And specifically to make sure that, of course, cylindrical cells have the benefit of having a couple of different standards, from 18650s to 2170s to 4680s and 46 class of.
So will there be the
diameters.
18650 standard of a pouch?
That is a conundrum, and that is actually, if you look real hard in terms of how China really got off the ground, is to be able to. Pouch cells, famously have no standard, and the pouch cell in your iPhone 1, 2, 3, 4, 5, 6, all the way to number in which we're now, all have a different product and different shape and different size, and that makes it incredibly hard to automate. And so, what is China coming in back in the day, realizing that the cylindrical game is dominated by the Japanese and the Koreans? Where should they play? If pouch cells and the flexibility of form factor requires you to have semi-automation, and labor was relatively cheap back then in China.
Interesting. Yeah.
That's where you play.
Interesting.
And so you really flex your flexibility muscle as a strategic entry point. And that's why, again,
and of course, driven by the end market, and a customer like Apple.
Yeah, exactly. And I think
to optimize the form factors to the millimeter, even to the 10th of a millimeter.
Actually, a good thought experiment, and I was talking to someone about this the other day. If you really look hard about where we are today in terms of the battery world in which we live, a lot of credit can go to Apple.
But the challenges that we face also are Apple's fault.
But I mean, you need a forcing function. You need someone. You need a visionary.
For sure.
Anyway, that's
who do you think is going to be the forcing function in the autonomy world?
I can't.
Can't say.
I'm not gonna say that out loud. But
Fair enough.
certainly there's going to be, I mean,
Yeah,
those
fair
are the
enough.
partners in which we want to grow with.
Right.
Yeah.
How do you think about the flexibility of your manufacturing footprint
So that coming
to
back
do different cell
exactly
designs?
coming back to that, it's no secret that we live in a high labor cost environment, and to really make manufacturing in the United States work, playing the strategy isn't prudent, right? Oh, we'll do this form factor for you, we'll do that form factor for you. That's hard. Other people in the defense sector have tried that, and you do get relegated to a very small market footprint. We just need to be able to play and strategically choose the types of form factors that we make, and then really iterate around chemistry and flavors. So it's really not the recipe of this sandwich analogy that I use maybe too much, of, you know, the bread and the lettuce and the other piece of bread inside of a lithium-ion battery. It's not so much the chemistry, whether you use rye or sourdough or whatever. It's really the shape of that Ziploc bag.
It's the Ziploc bag.
It's the Ziploc bag.
That your standardized Ziploc.
Yeah.
And then different sandwiches inside.
And so in the drone space, and I'm very excited and that SAE just came out with a new standard for Group 1, which is a smaller form factor or a lighter drone, SUAS, small unmanned aerial system, a standard for a pouch cell that is designed to be occupying the footprint of a series of 2170s. So it's 63 millimeters width by 140 millimeters in height. And that is obviously, I mean, it's no coincidence. It's 63 is 21 times 3, and 140 is 70 times 2. And we are part of that SAE committee.
Right.
And very excited to have really launched that as a new standard, the SAE JA 1016 footprint. Yeah, that's what we're tooling for.
Right.
And that allows us, with our 6 ppm right now and a lot more to come, part per minute manufacturing, that allows us to make 2.5 million cells of that form factor by middle of next year. And whether we we change the electrode coating to be thicker for higher energy, so you can have 340 plus watt hours per kg, or you make it ultra high power with thinner coatings for, 8C or 10C discharge capability, or even change out the chemistry altogether. Novel chemistries that the big behemoths don't want to touch because it's purpose built for these markets. Think LTO and niobium even. Those things that come after LTO for 30C discharge capability, which is relevant not just for kind of fast charging industrial warehouse robotics, but also for data centers in certain applications.
Yeah, I was curious your perspective on the titanates and things like that, which have found a niche in warehouse robotics. Is that, you think, going to continue?
Yeah,
that'll be standard lithium-ion flavors.
I think there is a strong play for lithium ion. Now, which flavor ultimately is going to be a technical selling point, and I think we have a good strategy for that. But it is your ability to handle multiple form factors, a select few, but be very adaptive on the chemistry that goes in, not just the design of the electrodes, but also the actual chemistry. And I think by virtue of that, you also accidentally become a company that has a tremendous wealth of know-how, and that is a value proposition I'm super excited for the future of EnPower. Is we'll be sitting on so much IP and know-how of how to actually do all this integration.
Yeah.
And the last kind of value add for us is, again, I think we've overinvested in the material space in the West so far. That is a benefit to us now, right? Because there are actually very few cell integrators at the end of the day that can benefit from all this. And so there's stranded IP, there's stranded innovation, and we are establishing partnerships and more will be coming, as we actually find a home for these innovations that are good, and American ingenuity and the Western ingenuity is there, but you have to have a commercial vehicle to actually have it serve an application at the end of the day.
Yeah.
And it might not be EVs or BESS in the beginning for
Yep.
some of these applications.
Yep. Yep.
And we are a pull through for that.
Very cool. Very cool. Yeah, I'm excited for what where you guys are going. What do you think about? Are you seeing the policy side of things, and maybe it's not even policy, but it's the interest that the U.S. government has on a geopolitical basis, playing a helpful role here?
I mean, I commend what the some of the policy movements so far have been.
Mhm.
That is yet another, perhaps one of the brightest stars that has aligned, that caused me to jump back in. This includes the NDAA, National Defense Authorization Act, Section 842 of FY26. Go read it if you're a geek. But that says that batteries procured by the military starting January 2028 not only cannot be manufactured in a foreign entity of concern, but also 95% of the bill of materials inside that cell also need to be sourced outside of a foreign entity of concern, and the technology itself cannot originate from a foreign entity of concern. Now, foreign entities of concern, of course, we know the four-ish, but China is the only one that is relevant in this case for batteries.
Mm-hmm.
And certain areas like the drone dominance program are a year ahead of schedule by a year. And that's great, because that is really the catalyst that allows domestic companies to stand up and actually have a fair shot at actually being able to serve these markets. And it is a strategic, it is a critical, it is a national security risk
For sure.
of a pipeline that is very easily with a tap that can be turned off. And so that is something that I'm really eager to serve at the awesome responsibility of building a domestic cell supply chain. And I think the DOW specifically have been very smart about right sizing that policy, right? They're saying 95% of the bill of materials are going into the cell. That's at CAM level, or the cathode active material level, or the powder level. Going too far is also detrimental.
Yeah.
If you said the lithium, even the lithium carbonate inside the cell can have never touched China, for example, if you said that, then, we might as well pack up and just go home.
Yeah.
Because you have to be prudent and practical. And of course, we're obviously going to be bleeding upstream as well as downstream, the policy and right sizing it for the moment. And also, I also commend the DOW for not making it domestic, but enforcing companies like myself to compete on a fair playing field with those in Korea, in Japan, in Taiwan. That makes sure that we are not just isolating ourselves in this, pat ourselves on the back kind of, we can make cells.
It's a great point.
You have to be still competitive on the global stage.
Yeah, it's
and that's a good, litmus test for us to say we are still world class.
Yeah. Interesting environment we're in. Maybe to wrap up, I wanted to just rewind a bit to a statement that you made as you were talking about your decision process to go back to EnPower. You said the world had changed in so many ways from the time you left EnPower to go to Stanford to the now coming back to EnPower. That was part of your decision
I never left,
process.
but yes.
You never left.
I left as an operating.
As on an operating basis. Could you sum up how you viewed the world then versus the world today, and what you think that means in terms of the opportunities for not only, we've talked a lot about EnPower, but just like the industry at large?
Yeah, I mean, I think just as fashion trends do, technology trends also overswing. And I think that was a moment when I stepped away from being an operating role in 2022, where I think we all recognize we did overswing a little bit
Towards
the full electrification of everything. I think that is eventually going to come, but there's a pace at which is right. And we're naturally going to be overeager. And that was just the kind of beginnings of going too far and then sucking back in. And I think the timing for me, personally, transitioning out temporarily, if even, was the right decision to make. Obviously, I'm very thankful to my entire team for fighting the good fight and riding through the choppy waves as I pursue this intermediate journey. But we are in a world now where sovereignty of supply chain is more important than ever, because it is not just a preference, it is a threat. It's a threat environment.
Which makes it a requirement.
There is a new wave of critical technologies from, back in 2022, that was the war in Ukraine has just started, right? And of course, we've seen what drones can do and reinvent the modern theater of war.
Yeah.
But that was, we were just getting a flavor of that.
Yeah.
But now that is fact. And that is just the start of robotics, of flying robots. But we're now also seeing this new wave of critical technologies.
Physical AI, humanoid
Physical
robots.
AI. And of course,
all this.
Dare I say, data centers, of course, that is driving a tremendous amount of growth. And that is the dust is gonna settle.
It is a great point you make, though, that and I haven't really thought about it to the level of depth that you have, but in that time period, which that's 26 now, right? And so from 2022, 2023, in the last 3 or 4 years, you've seen the emergence and the 10x of importance of multiple verticals that were nascent before for batteries. Before, it was basically consumer electronics, mobile electronics, and cars. It's basically it, really.
Yeah.
And then you've seen in this time frame, we talked about grid storage wasn't really a thing.
Not sexy back then.
Data centers, drones, and now, let's call it ubiquitous autonomy.
Yeah.
These are all giant industries, or will be on their own, each one of which is critically dependent on a specific battery technology. So
right. There's no better time
than
to be
now
building.
to be in the battery space.
So I'm now a fish in the stream alongside you.
Yeah.
Good luck.
Yeah, to you as well. Hey, I very much enjoyed the conversation, Adrian.
Likewise.
Thank you for taking so much time to spend with us, and definitely appreciate the work and the continuing work that your team is doing at STEER. And I wish you all the best with EnPower. And
Thank you.
We, as a country and as a world, need companies like that to succeed.
Right. Likewise as a peak.
Thanks again.
Thank you.